Welcome to this demo on automating flight planning under wind hazards using large language models. This work is a collaboration between George Washington University, Duke University, and MIT Lincoln Laboratory. The focus of this research lies in developing a robust, intelligent system that can adapt flight paths dynamically to mitigate the risks posed by wind hazards. By leveraging the power of large language models, this approach enables a safe, efficient, and human-centric flight planning, ensuring both operational reliability and energy optimization. Let's look at the overall architecture of our flight planning automation framework. Here we have the wind hazard prediction. Then we'll use our customized A*STAR flight planning algorithm to generate a diverse set of flight plans. Each of these flight plans will have a certain number of features. These features then will be augmented with system messages and a user prompt from human operator to generate a bunch of weights that determine the importance of each feature based on the flight operator preferences. We also ask our LLM to generate a reasoning for its decision for better interpretability purposes. Then the score of each candidate flight plan will be computed and the best one will be selected and recommended to the flight operator for their final review. Here is the wind hazardous region in Dallas-Fort Worth area. There are 4 different set of wind hazard polygons, each noted in a different color, and each set represents a particular altitude. Origin and destination is demonstrated in green and red colors. Let's look at some examples. Here, we tested the flight assistant with 2 classes of prompts, explicit and implicit. In explicit prompts, the preferences of the flight operator is clearly mentioned in the prompt and there will be a direct reference to the feature name. For example, here, the operator wants to minimize the number of waypoints and energy consumption, and other features are not important for them. Then, the assistant will generate the weights, the final selected flight plan, and a reasoning for its decision. In this particular example, the flight assistant will assign 0.4 and 0.6 weights to energy consumption and number of waypoints respectively, and flight number 13 is selected. Also, an explanation is provided if the operator is looking for the reasoning behind this decision. In the following, there are more examples of explicit and implicit prompt from an operator with the flight assistant. Once the optimal flight plan is selected based on the operator's preferences, it is recommended for their final review. On map, the blue line represents the direct flight path from the origin to the destination. The red areas highlight regions where the flight intersects with wind hazard zones. The green line shows the rerouted flight plan that avoids these hazardous areas. In conclusion, this work successfully integrates multiple tools, such as wind hazard forecasting, flight route generation, and energy consumption estimation, within a novel flight planning framework that utilizes large language models. By optimizing flight plans based on human operator preferences, This approach ensures safer and more efficient flight operations, particularly in the presence of wind hazards. The inclusion of LLMs allows for enhanced interpretability and user interaction, positioning this work as a pioneering effort in the application of AI within aviation. Moving forward, further improvements to prompt interpretation and the integration of real-time data will continue to enhance the effectiveness of this system. Thank you for watching the demo.